All right, today's lesson is a throwback to geometry. We're going to cover the Pythagorean theorem and common Pythagorean triples. When solving for missing sides of right triangles, we really have four options. The first two are what we're covering today. So revisiting the Pythagorean theorem and looking at Pythagorean triples or multiples. In the next few days, we're going to go back to our special right triangles and then get our refresher on basic right triangle trigonometry, SOHCAHTOA. So first up, looking at that first method, Pythagorean theorem. So looking at this right triangle, we should know that the perpendicular sides here and here, those are the legs. Okay, the longest side is always opposite the right angle. So opposite the biggest angle is the biggest side. This is the hypotenuse. And Pythagorean theorem, as we all know, is a squared plus b squared equals c squared. All right, so the a and the b are the legs. The c is the hypotenuse. Okay, I also have a little shortcut for how to get to the hypotenuse a little bit faster. So if I rewrite the structure of Pythagorean theorem, a squared plus b squared equals c squared, I want to solve for c. So I'm going to rewrite it with the c squared on the left. And then I take the square root to unlock the square, right? So I take the square root of each side. This is like a package, so I can't unlock those individual components. It stays as c, right? Technically it's plus or minus, but c is a measure, has to be positive. C is the square root of a squared plus b squared. And again, a and b are the two legs. So this helps me get to the hypotenuse just a little bit faster. Okay, if I want my shortcut to find a leg, I could be solving for either a or b. Let's say that I say a. So again, let me just rewrite the structure of Pythagorean theorem. And then I want to solve for the a component. So I'm going to subtract the b squared to the other side. So a squared equals c squared minus b squared. And then to unlock that square, I take the square root. What I do to one side, I do to the other as well. I can't unlock those individual components because that's a package. It's like we have parentheses around that group underneath the radical. So now a, technically plus or minus, but again, has to be positive because it's a measurement. My leg would be equal to the square root of the hypotenuse squared minus the known leg squared. So again, this is the hypotenuse, my longest side, always opposite the right angle. And this would be the leg that I do know. All right, gotta love beautiful shortcuts. Okay, next up, a whole batch of finding the missing side. All right, simplify any radicals as well. So in this one, I want the hypotenuse. So let's say I do it the longhand way. A squared plus b squared equals c squared. Again, those are my legs. This is my hypotenuse. So I know that 3 squared plus 5 squared equals x squared. Okay, so 9 plus 25 equals x squared. X squared equals 34. I unlock that square by taking the square root. Technically, x is plus or minus the square root of 34, but since that's a measure, it can only be the positive. So x equals the square root of 34. I can't simplify that. That's 2 times 17. I don't have any pairs. Final answer. Okay, my other option is to use that beautiful shortcut that I just taught you about. So let me remind you over here. So here I know that my hypotenuse, x, is the square root of this leg squared plus this leg squared. So 5 squared plus 3 squared. 25 plus 9. You can see how I'm going to get to that root 34 just a little bit faster. I don't care how you do it, as long as you get the square root of 34. Okay, for b, same thing. Let's say that I start with the Pythagorean theorem. So a squared plus b squared equals c squared. Here I have one leg, and here I have a hypotenuse. I want that longer leg. So I'll say x squared plus 3 squared equals 13 squared. X squared plus 9 equals 169. Take away the 9. X squared equals 160. Take the square root of each side. 160 is 16 times 10. So x could be plus or minus 4 root 10, but really has to be positive because that's a measure. So x would be just 4 root 10. Let's check the shortcut, see if it gets us there faster. Okay, so solving for a leg. So my leg is equal to the square root of my hypotenuse squared minus my leg squared. So 13 squared minus 3 squared. There's my 169 minus 9. Square root of 160, right? We just simplified that. 16 times 10 gets me the same, 4 root 10. All right, either way is fine. Plug into Pythagorean theorem or use the shortcut. It just depends. Are you solving for a missing hypotenuse? In that case, I'm looking for my hypotenuse as the square root of one leg squared plus the other leg squared. Or are we solving for a missing leg? In that case, this leg is equal to the square root of the hypotenuse squared minus the leg that I know squared. All right, next 2. So looking at this one right here. Now I could use Pythagorean theorem, I could use the shortcut, but I could also use my knowledge of similar triangles and shrink it down. Let me show you what I mean. So when I look at the 2 sides that are marked, I can see that they're both divisible by 4. So let me draw a triangle that is similar, but I'm going to divide each of these 2 known sides by 4. That would give me a leg here of 1 and a leg here of 2. Let's say that I make the hypotenuse y. So these triangles would be similar. They're the same shape, they're different sizes. I've just shrunk it down temporarily. So it gives me smaller numbers to work with if I want to solve for my hypotenuse. So if I use my shortcut, I know that my hypotenuse is equal to the square root of 1 squared plus 2 squared, which is 1 plus 4, which is root 5. Okay, so this measure here would be root 5 for my shrunk down triangle. But if I want to enlarge it back up, I want to grow it back up, right? Scale it larger. I know that 1 times 4 is 4, 2 times 4 is 8. So root 5 times 4 would be 4 root 5. X is 4 root 5. Right? All I did was multiply by 4. Now, could I use these numbers in Pythagorean theorem? Sure. I just have to simplify my radical with bigger numbers. Let's try that same process here. So let's say that I shrink this down because these 2 sides are both divisible by 6. So if I divide each of these by 6, I get a 1 here, I get a 2 here. I'm going to call the side y temporarily. So now, Pythagorean theorem, the shortcut, I'm going to say that my leg is equal to the square root of my hypotenuse squared minus that known leg squared. So 2 squared minus 1 squared, 4 minus 1, I get root 3. So this would be root 3. So now to enlarge it, to make it bigger, to make it grow back into this triangle, this gets multiplied by 6. This gets multiplied by 6. So this has to get multiplied by 6 as well. So this side would be 6 root 3. X would be 6 root 3. Okay, one more thing to point out, just to foreshadow where we're heading with this. I'm going to remind you about a special right triangle. This particular one is a 30, 60, 90 triangle. We use them a lot in geometry. When it's a 30, 60, 90, the short leg is x, the longer leg is x root 3, the hypotenuse is 2x. So if I had a short leg of 1, this would be root 3, this would be 2. In my example here, this is my short leg, 6, multiplied by root 3, there's my longer leg. Take the short leg and double it, there's my hypotenuse of 12. It fits the pattern. We're going to deal with this one in the next few days again. Okay, last set. Here I'm solving for a missing hypotenuse. My 2 legs are the same. It's an isosceles right triangle. Let's use the shortcut. My hypotenuse is equal to the square root of 4 squared plus 4 squared. So square root of 16 plus 16, square root of 32. 32 is 16 times 2, so I would get 4 root 2. Okay, this triangle right here is also a special right triangle. Let me write that first. Sometimes we call it an isosceles right triangle. Other times we just say it's a 45, 45, 90. Okay, the pattern here is that the 2 legs are the same, and the hypotenuse is a leg times the square root of 2. Let's see if it fits the pattern. These are the same, and then 4 times the square root of 2. That's what we solve for using Pythagorean theorem or the shortcut to get to our hypotenuse. Okay, one more over here also, just a little note to self, also an isosceles right triangle or a 45, 45, 90. Because I have 2 legs that are the same, they're x, hypotenuse is 6. Okay, so then let's say that I plug this time back into Pythagorean theorem, give you a variety of ways of solving. X squared plus x squared equals 6 squared. 2x squared equals 36. Divide by 2. X squared equals 18. Take the square root. X would be plus or minus. I know that that's 9 times 2, so 3 root 2. But again, can't be negative. Only taking the positive. Okay, let's check that pattern. If the 2 legs are the same, they both be 3 root 2. The hypotenuse should be x root 2. So if I take 3 root 2, and I multiply by root 2, that would be 3 times 2. That would get me back to 6. That pattern holds. All right, flip to the back. Okay, these two just incorporate some algebra. So can you solve for x? Simplify any radicals. So here again, we're just going to plug straight into Pythagorean theorem. In both of these examples, we see an x in multiple places. So I'm going to go straight into that structure. So x squared plus parentheses 2x as a quantity squared equals 10 squared. Most common mistake is forgetting to write the parentheses here because the exponent applies to the 2 and the x. So next stage I have x squared plus 4x squared equals 100. Combine those like terms. So 5x squared equals 100. Divide by 5. X squared is 20. Take the square root. 20 is 4 times 5. So I would get plus or minus 2 root 5. But again, I can't have a negative. So only the 2 root 5. Okay, one more that has a little algebra. So here my two legs are binomials. So I need to make sure I write those in parentheses. So that binomial squared plus x plus 2 quantity squared equals the square root of 65 squared. Whenever I have a binomial squared, I want to visualize it as two separate binomials multiplying out. It's a good visual reminder that we have to FOIL it. If I square a square root, that gives me just the radicand, the number underneath, the 65. So now when I FOIL this out, my first, my outer, my inner, my last, I have x squared minus x, so minus 2x plus 1. Do the FOIL here too. So x squared plus 2x plus 2x, so plus 4x plus 4 equals 65. Okay, combine your like terms. So I have these quadratics, 2x squared. My linear terms, I have plus 2x. My constants, I have plus 5 equals 65. Okay, I'm going to pull to one side, subtract that 65 over, and I'm going to solve it by factoring. So first glance, I have a GCF, so divide out the 2, leaving behind an x squared plus x minus 30. Okay, here, basic quadratic trinomial, what multiplies to negative 30 that adds to 1? Right, we know it's got to be 6 and 5. And the 6 is the positive, the 5 is the negative. Set each factor equal to 0 and solve. We get that x could be negative 6. X could be positive 5. But can it be negative 6? If I plug it in here, this side would have a measure of negative 7, and we know that that is not possible. So the only solution that works is that x equals 5. All right, one last skill, method 2, looking at common Pythagorean triples. So here is a partial list of common Pythagorean triples. And all that means is that these are right triangles that have integer side lengths. And there's really infinitely many Pythagorean triples that exist. These are the ones that show up the most often, that have the smallest values for the sides. What I wanted to model for you, since I'm looking at common triples and multiples of common triples, is I'm going to look at the smallest one, the most common one, the 3, 4, 5. And I've drawn that out for you here. So it's pretty common to see a 3, 4, 5. We know that 3 squared plus 4 squared equals 5 squared. So again, I can look at multiples. I can apply a multiplier to the 3, 4, and the 5 and create similar triangles, right? I said that on the other side. let me write it here. I can create multiples where I have triangles that are similar. I can take this triangle, I can scale it up, I can shrink it down. That means that the sides are proportional. They have the same ratio and the angles are congruent. So let's say that I wanted to make it bigger. Let's say that I wanted to double all the sides. Apply a multiplier of 2. 3 doubles to 6, 4 doubles to 8, 5 doubles to 10. Right? There's a new Pythagorean triple, but really it's a 3, 4, 5 times 2. Sometimes we shrink them down. So let's say that I apply a multiplier of 1/2. 3 times 1/2 would be 3 halves. 4 times 1/2 would be 2. 5 times 1/2 would be 5 halves. Okay, one more variation. Let's say that I apply a multiplier that has a root. Let's say that I multiply all the sides by the square root of 5. So here I would have 3 root 5. Here I would have 4 root 5. And then here I'd have 5 root 5. Okay, so if I start with any of these common triples, I can apply a multiplier to make it grow bigger or shrink it down. But essentially, those triangles are similar, so it just creates for me a new triple that I can work with. It also just helps me solve for missing sides easier and faster, more efficiently. So here in example 3, it's all about common triples and multiples. So when I look at this first one, I can see that these 2 legs, I could shrink it down. Let's say that I visualize it shrunk down. I could divide the 10 and the 24 by 2. That would make this 5, and this would be 12. Okay, so then I can see that really to grow back into this triangle, I just have to apply that multiplier of 2, right? 5 times 2, 12 times 2. And I recognize that this is the common triple of 5, 12, 13. So if I want x, I have to double that 13 to get to 26. X is 26. Okay, over here I'm going to do the same thing. I'm just going to shrink it down. Okay, I can divide each of these, well, I know by 5, and that's it. So 35 divided by 5 is 7. 125 divided by 5 is 25. Okay, so I know that to enlarge it back up, I'm going to have to apply that multiplier of 5. And I recognize this right triangle as a 7, 24, 25. So if I multiply the 7 back by 5, I'm here at 35. 25 times 5, I'm at 125. So 24 times 5, I'm at 120. X is 120. Okay, one more row and we're done. All right, so here, let's see. Here I have a fraction. So this one I might enlarge it instead. Right, if I don't want to deal with that fraction, to enlarge it, I could double all my sides. So if I double this 15 halves, I'm at 15. And I double that 4, I get 8. Is that a common triple? Yes, that's the 8, 15, 17. Okay, but to go back, to shrink it down, I need to apply the multiplier of 1/2, right? Because 15 times 1/2 is the 15 halves. 8 times 1/2 is 4. So 17 times 1/2 is really 17 halves. I can write it like that, no problem. You want to write it as 8.5? I will take it that way too. 8.5, no problem. Okay, last one here. Okay, here I can see that they're all divisible by 3 and by root 7. So if I shrink it down, divide out a 3 and a root 7, I'd have a 29 here and 20 here. So I recognize this as that last common triple that I've put on our list, that this must be 21. It's our 20, 21, 29. But I've applied a multiplier of 3 root 7, right? 20 times 3 is 60, but also times root 7. So I get 60 root 7. 21 times 3 root 7 is what I'm solving for. So that must be the 63 root 7 right here. And if I double check that hypotenuse, I know that 29 times 3 root 7 gets me back to that 87 root 7. So my missing measure for x is 63 root 7. All right, hopefully a good refresher of Pythagorean theorem, a few shortcuts to get to legs and hypotenuses faster, and then also returning to the common Pythagorean triples and their multiples. Have a good day.